In this video, we're going to look at atomic spectra and determine what types of atomic transitions between energy levels are allowed based off of the properties of the two electronic states as determined by the quantum numbers in their term symbol. So we have our initial state here with a 2s plus 1, its multiplicity, the spinning or momentum quantum number s, capital S, and orbital angular momentum quantum number capital L, and total angular momentum quantum number J for the total term symbol for a given state. And then it transitions to a state with a term symbol which has 2s prime plus 1 L prime J prime for its term symbol. So the quantity s prime minus s is going to be the change in the spin angular momentum quantum number, delta s. Change in the orbital angular momentum quantum number L is going to be L prime minus L, and same thing for the total angular momentum quantum number J. It's going to be J prime minus J is going to be delta J, our change in each of these numbers during the transition that it undergoes from one electronic state to another. And that's going to be also during the process of absorbing or emitting a photon, going up or down in energy. Okay, so what are our selection rules for this process? Selection rules just saying what are the rules about how these quantum numbers can change. What are the values of delta S, delta L, and delta J? Well, delta S has to equal 0. Just like with the hydrogen atom, we have to have our total spin stay the same, so our electrons are not going to flip spin during these types of absorptions. And for our value of delta L, we can have either 1, 0, or minus 1. So it can change at most by 1, but there's also the caveat that you cannot transition from L equals 0 to L equals 0 in another state. So L can stay the same as long as L is not S in both cases, or L equals 0. Okay, then for J, we have the same rules as for L. We have 1, 0, and minus 1, but you cannot transition from J equals 0 to a J equals 0 state. J has to change if your J equals 0. Okay, so with these rules, let's look at some examples for what types of transitions would be allowed. So if we first look at the simplest term symbol, singlet S0, S equals 0, L equals 0, J equals 0, for our multiplicity being 1, 2s plus 1. And in this case, since our delta L and delta J can't be 0 because we're already in 0 for both of them, and these values are greater than or equal to 0, we have to have delta L and delta J equals plus 1. So that's going to push us to a P state with J equals 1, and our multiplicity and spin has to stay the same, so we're still going to be in a singlet. So our only transition we can have from singlet S0 is into singlet P1. Any other transition violates one of these rules right here, or violates the possible values of S, L, and J. Okay, so that was simple enough. What about if we have something like a doublet S 1/2? Okay, if we've got a doublet S 1/2, then we're going to transition to a state which is also a doublet. And we have L equals 0. J doesn't equal 0 now, but L does. So L has to transition from an S to a P up to L equals 1. Then J can either stay 0. It could decrease by 1, but J has to be greater than 0, so we can't have minus a half. Or it could increase by 1, so we could have 3 halves. And it's perfectly valid to have a state of 3 halves for a P state, for a doublet P. So we could either go doublet P 1/2 or doublet P 3 halves. Two possible transitions out from a doublet S 1/2. Okay, moving on now to bigger and better things. Let's look at what happens if we have a triplet P0. Okay, so if we have a triplet P0, we have to transition to a state which is a triplet, so delta S has to stay 0. Delta L can be 0, so let's say it's a P state. Then what about J? J is 0, so J can't stay 0. J has to change, and it can't go down. It can only go up because it has to be greater than or equal to 0. So triplet P1 is the only P state that we can transition into there. And let's see. We could go down in L, and we could go up in J. Let's see. Triplet S1. Not sure if there's actually a state that's possible to do that in, but according to the rules I have listed out here, that doesn't seem to be illegal. So for now, I'm just going to mark this as okay, unless I find out later, in which case I'll put an annotation saying that's a no-go. Okay. Then additionally, we could also transition up in our value of L. We could have triplet D, and then we could increase by 1 as well. That would be a valid state. That's a valid choice of J for a triplet D state. Okay, so let's do one more example, which is going to have a crazy number of options. Let's do quartet F 7/2. All right. So let's start by going up. We have to stay quartet. We have to keep S the same. We can go from F, which is L equals 3, to G, which is L equals 4. And we can keep J the same. That's fine. Quartet G 7/2. Let's see. G equals 4, so having a value of 7/2 is okay if we have a quartet there. That should be okay, according to our rules from previous videos. All right, we could also have quartet going up to G, and we could have an increase in J, 9/2. That is also a possible value of J for a quartet G state. You got to make sure that even though if your value of S and L is allowed, you got to make sure your value of J is allowed as well. Okay, then we could stay the same. we could transition to another quartet F 7/2 state. That would be delta S, L, and J all equal 0. We could go to a quartet F 5/2. F equals 3 quartet, so that's also legitimate. We're still good. We couldn't transition down to a quartet F 3/2. That would be a delta J of 2. Okay, so it looks like we've got all of those. Could we go to a quartet F 9/2? Well, F is L equals 3, and for a quartet we have S equals 3/2. So 3 times 2 is 6, plus 3 is 9. So if we have our L plus S for a quartet F, S is 3/2, L is 3, so that is 9/2. So it appears that that is an allowed value of J as well. Okay, then continuing on, we could have a quartet where we decrease our quantum number. We could have a quartet D. D is L equals 2, so that's 4/2 plus 3/2. So the largest J we could have is 7/2. So we can't do our increase in J here. That wouldn't be allowed. That would be, you can't have a quartet D 9/2. That's not allowed by the rules for what J can be. And we could also have a case where we have delta J equals -1 in addition to delta L being -1 for a quartet D 5/2. Okay, so you see, depending on what our term symbol is, we can have quite a lot of possibilities for what type of other electronic states it can transition to based off of their term symbols as well. So it's just something you can find out for a given term symbol what the values of S, L, and J are, and then list out all the possibilities and see if they are valid term symbols according to the rules of term symbols. Most importantly, remembering to note that, L plus S greater than or equal to J greater than or equal to absolute value of L minus S, and J, L, and S must all be greater than or equal to 0.